Na, mehet elvileg. Szóval, I am Richard Tier from Magos IT KFT, and I want to talk about optimization building blocks. It's a know-how transfer or presentation if you want. So what will be the contents? There will be some motivation, there will be some checks for heavy operations, when to do that, some space partitioning looking like things, then minor algorithms, minor things. When I call something minor things, it's usually a prerequisite for the further algorithms, and they are just smaller. I also want to put some part into this presentation when we are not talking about that complex things, so we can lay back a little bit, and then again we start to talk about more complex things. So after those minor things, we talk about Smallgorithms, which is actually a name. Various heaps, because that's a more complex topics. There will be another minor things afterwards. Proximity groups, collision detection engine, and in the very end I will talk about something of a different nature. It's basically a debugging tool. So all of these are related to performance and building blocks to do algorithms and geometry algorithms or graphics, where these can be used as building blocks for very performant code, except for the number 10, which is the end. But that is really useful for debugging these kind of algorithms and also yours. So I hope that will be also useful. So about the motivation. The first and foremost motivation is code reuse. So I am presenting the possibilities. Basically, what my biggest aim with this presentation is that you know about these kind of building blocks. There are countless others, but at least you should know about these building blocks. And also, not just the building blocks, but the way you can Lego and put them together. The other motivation is performance, because the building blocks presented here are usually scalable for big number of data, and also, of course, good. So you should use this if you have a problem that you identify that these are solving it. So usually these are big O(n). I hope you know the big O notation, and better algorithms sometimes even better. Also, I tried to make these good abstractions. They are generalized, documented. When I mean documented, they are having in the source code base of course, they are having documentation comments, even documentation, not documentation, but regular comments in the like the lines of the algorithm itself, not just for their functions. So it's well documented. Also, this will serve as part of the documentation. And they are also not just generalized, so you can use it for a lot of objects and a lot of use cases, but also parameterizable, fine-tunable. So you can fine-tune those. But that's a double-edged sword, because if you leave a lot of parameters and a lot of fine-tuning, then using the algorithm is becoming slightly less enjoyable. So it can be paralleling writing your own or something like that, or thinking out your own. So I also try to present sensible defaults in all the cases, so it's simple to use. And the last motivation is that geometries is just too huge. Currently, almost code reuse is coming from that part of the code, and I value it. I also use it. I just didn't want to put these into geometries. I could do that, but this is better separated, and I would advise to have separations like this in the future too. So to recap, the biggest motivation is that you get building blocks that you can put together. And whenever you are having a problem, you face a problem, and you identify, oh, I can use this building block, then you are fine. And you have something on your hands which is really fast, scalable, it will go even if you are having a very wide world or a big scene. So let's get started on HeavyOpCheck. Actually, I can start to explain this in this image. I hope you see the mouse cursor, but if not, just look at the left image. What you see here is multiple frames, like multiple rendered frames, and they are after each other, layered. That's how I draw it. You don't think anything fancy, just that's how the drawing is. And you see that there are also in the vertical direction sizable amount of chunks, and the vertical direction represents the frame time, like how much time it takes to render that frame of a game, of an engine, of an application. And as you can see, I just put three things here, two heavy operations on the top, and also just something that I term others. Others is something that you need to do every frame anyways. Just I term it others because we are not talking about that much in this presentation, in this part. So just others, you always need to do that. But you are having two heavy operations, A and B, heavy operation A and heavy operation B, and as you can see, they are measurable, they are nearly as heavy as all the other operations at all. And as you can see here, they are happening every frame. And what we want to do is that if we add, we have maybe 5 of those, not just 2 of those, and these heavier operations add up very quickly. And of course, then you will have FPS drops, low frame per seconds. Your application will be slow, stuttering, because there is a lot of things to do. So what we want to do with this is that spread these heavy operations to multiple frames, so that it's not always happening in the same frame rendering time. And of course, you can only do this if indeed you can do this. Like if a heavy operation, let's say a heavy operation is that you have the camera or the player moving around and you want to cache some data around it. And actually, maybe you are doing that every frame now, but that's not sensible. You can do it every 5 seconds even. And then there is some other heavy operation, I don't know, some big calculation of something that you also do in every frame, but you realize that, okay, we can do it in also in every 5 seconds, but that's bad because then everything will be smooth, and then in the 5th second, everything is slow again. But what we want is that, as you can see, the frames, some heavy operations happen in some frames, some heavy operations happen in some others, and try to spread them around. So that's our goal. Spread the heavy operations to different frames, it is possible. And of course, this means that it's only possible if we do not need to do these heavy operations every time, just every X milliseconds. And we could calculate frames here, but milliseconds is more humanly making sense. You can it's more in line of your thinking. Is this algorithm going to work? Is it tolerating that I do this every 500 milliseconds, or is it not? And I always, for all these tools I'm presenting here, I always tell where in the code base this is. Of course, you can maybe stumble on this presentation from some other source. I don't know how the future will be. So you have no source codes, but I think it will still make sense. But for those who are working in this code base, this is where you can find it. HeavyOpCheck it's called. So a case study, we have A, B, C heavy operations, and they are not going to be calculated every frame. And the HeavyOpCheck like solution would be operation A happens in every 1.1 seconds plus some randomization. That's a thing. Operation B happens every 1.7 seconds plus some randomization, and operation C happens every 2.1 seconds plus some randomization. And with this setup, all of them usually fall into separate frames, and thus we are avoiding lagging. We are having a better throughput, everything is more smooth. Yeah, I also mention here that the milliseconds I choose prime-like numbers. Of course, in milliseconds they are not primes, but also not in seconds. But you see what I am doing with this. So I try to make it so that they are more rarely coinciding, if it's possible. But that's not really that much needed because there is a randomization that I was not talking about yet. But there is also a randomization that happens not just once at the start for calculating the schedules, but at every scheduling it happens, this randomization. So it's pretty much nearly impossible that more than a few heavy operations end up in the same scene. And of course, in the example, this was only 2 operations or 3, but in real life you might have maybe 10, and all you want to know is not that there is no 2 at the same time, but that there is no more than 5 or something, and then everything will be going constantly with 60 frames per second and every lower and devices and everything. So, okay, so how we are doing this, or how you are using this, you have this constructor in the HeavyOpCheck that you put in the frequency. Also, you can say the randomization range, but that's having a reasonable default. And you can also parameterize if you want the thing start at the very first occasion that it's possible or not, or if it will be started on the next scheduling point. Yeah, but how is this? Like, of course, there are default parameters. That's really sensible. You can maybe not even do anything, just call this and create an object. But how you tell what to do? What is the heavy operation? Like, how this works? You construct this object and what to do with it. I call it heavy operation check, not heavy operation, because the heavy operation is what you are doing. It's the code that already exists. It's in your code base. It already exists. It's doing what it's doing. You just measure that it takes too long when it is happening together with something else. So this is just a check. You create a check with this, and you can ask this check, should I do this heavy operation now? Oh, so there is no queues in this, there is no fancy threads in the background, anything. You just check if there is the time for doing this heavy operation. And as you can see, there are some parameters here which are completely optional. I always try, as I said before, to make sensible default parameters. And also the parameters further back behind are the ones that are least possibly used in the usual cases. So it's just how this logical to plan an API or design an API. So there are also a parameter that you sometimes want to use. Actually, I use this a lot. That I ask if I should do this heavy operation, but here you can provide some condition, of course a boolean, but here you usually write a condition yourself that I want to force the heavy operation regardless if it's scheduled or not, if this condition is true. So that's a very common use case. You can do that with this. And you also, this is a really rarely used case, so that's why it's the last parameter. You can tell not to update the bookkeeping. So that maybe you force heavy operation, and if you update the bookkeeping, the next schedule will be like 5 seconds from now if you have the 5 seconds scheduling plus some randomization. And maybe you don't want that. You want to keep the original schedule as it is for some reason. And then you can say false to here. I used it somewhere, so that's why it's implemented, but you don't need to use that anymore. There are further possibilities. That was what you saw before is what you are calling, who designed the heavy operations. And these others are actually what others are calling for you. Like, maybe someone can say, okay, I need your operations now because, I don't know, some other component wants it as fast as possible. So there is this force next should do, then it will, the thing will return the schedule will move back. So it will happen anytime you ask, like next time. And there is also this operation has been done before now. You can tell that some external magical force have done the operation that you intend to do, so you don't need to do this anymore. And this basically just moves the scheduling away from now. This is handy in some cases. I use it for performance reasons, but it's a rare use case. I just wanted to mention it. So what is more relevant, an example. This is how you create two kind of heavy objects. As you can see, I just created these as class variables because I don't intend to change these, so this can be a class variable. Here, this is taken from real code, two heavy objects, and one of the checks is happening every 400 something milliseconds, and one is every 1.5 seconds. So they are pretty far away, plus there is the randomization always. So they usually will not happen on the same time, but one of the checks need to happen more often than the other, because that's how it came out for my use case. And how I use it, for example, this is also taking an example from the same code. We just put an if statement, and in the condition we are saying, this heavy operation, should I do this? And here you are even seeing an example that, okay, there is these other two conditions. If this is proper and true, this is hold. If these two things hold, I should do it definitely. I don't care about the scheduling, I should do it then. Like if the level changed, I need to re-update the caches or something. If a camera moves too far, this is actually in line with the example I said. So if the camera moves too far, I need to do the operation again. And your heavy stuff is just the code that you've written, it's there, it's in the middle of the if statement, in the body of the if. You just put it there. Of course, if you are making it clean code and fancy, you can put a function call here, it's maybe more clean, maybe it's very small code and this is just how you do it, maybe it's performance critical, then you don't want the call, it's just simple to use. But there are some caveats, because beware, if your single heavy operation is really heavy, it is so heavy that it cannot happen in any frame, because it's just slow. This doesn't help, of course. Actually, it makes things more worse in a way, because if your heavy operation is too heavy and you are having a low frame per second, if the single one is too heavy, it's not the mix of the operations that you can spread around, but there is one big that is so heavy. And if you try to do it with this, you will get a lot of frames, like maybe 5 seconds of time when everything is going smoothly, there is no lags at all, 60 frames per second, everything is fine. And then there is this frame when the image stops, it calculates for maybe 3 seconds, because that's how slow you wrote that code. It gets stuck like that, the user is having no idea what is happening, then for 5 more seconds it will be very, very nicely going again. And it stutters like that. So you should definitely avoid that. This is not for that heavy operations that cannot fit in a single frame. This is for those that can fit, but when mixed together with others of the same size, they can like add up together. So yeah, that's about it. And of course, if you need to do something every frame, then this is not a solution, because however you schedule it, you need to do it every frame. Okay, in the future, maybe a multi-frame heavy operation would be nice, like a coroutine-like thing. But for now, you can also get around with using asynchronicity in the background if the operation itself is so heavy. So let's go and start another topic. I hope it was easy to comprehend. I hope you saw what's the point. The next one will be TemporalSpaceCache. I call it space partitioning without partitioning. So let's talk first about the space partitioning a little bit in general. What's the aim of space partitioning? You have this very big scene a very big word, a big level, or big something, a lot of objects in a big space. But you want to avoid addressing all of the objects. You need to make some questions, like which is so close to me that I might collide into it, or something else, I don't know. Which is so close that I can at least animate it, because they're very far away, so maybe I don't even show, and so on. So those kind of questions you want to calculate locally, because if you ask those kind of questions for all the objects, then it will be even slow if your algorithm is linear, because just the object's number is too much. But if you calculate locally and only consider elements that are close to you, that is very good. And if you have x number of elements and y number of partitions, then likely, and of course this expects random distribution, like in many cases we will expect in this talk, x per y elements will be in your little partition, if you partition the space into little cubes or spheres or whatever. So this is basically grids, quad and oct trees, other kind of trees, skip lists, whatever trickery. And this is well known, but there are some issues with this. The first is that you might need to refactor code a little bit much, like too much. So that if you are not having this space partitioning scheme for your object scheme, there comes this problem that how to refactor it effectively so that it's easy to add. The easiest way is to duplicate representation when you need it, and then it can quickly add up, because then you will have this other solution, and it also needs some kind of space partitioning. It implements its own kind of very own space partitioning. Then this other is also doing the same, and it adds up, and it's getting huge. And also it can desync maybe, and lead to bugs and all kind of stuff. It's really hard to maintain and so on. So, despite these are really fancy and cool, oak trees, grids, and all kinds of stuff, it might hard to add to some existing code. And I wanted to get around this. Basically, this is the most thing that I wanted to get around. And the idea is to create not a space partitioning, not a partitioning, but a cache. A space-time cache. Not just a spatial cache, but a space-time. And that sounds really sci-fi, and it also sounds a little bit Back to the Future-ish. But it's really what it is, because the point is that it should always contain the things, whatever the things are, that you are close to right now. So there is a temporal part to it, and there is a spatial part to it. And then you should not even consider things that are far. And let's imagine that this is somehow magically updated for now, because this is just the idea now. And I tell you where it is, so of course it's not just an idea, but it is existing solution. So it's in TemporalSpaceCache. Performance, utils/performance/TemporalSpaceCache. Okay, how we do this? We should have an origin. That's where the algorithm starts. What is the origin? It's like, imagine it being the camera that moves. If you need to consider things against the camera or the player. Or maybe imagine it an object that you are moving with the mouse, like the user is moving an object with the mouse, and it wants to snap this object to some other objects. You know what is snapping, that if you move it close enough, it snaps there. You don't need to very thoughtfully move the mouse, but it automatically snaps to it. So maybe you want to consider what to snap to, but of course only the local area, not all the world you want to consider. So this is the origin. These things I call origin now. We also have two areas. We have the cached area and the keep area. I guess you can imagine what the cached area is. It's a cached part of the world. And when you do your operations, you of course only work on your local cached part of the world, not the whole world, but only on this small thing, which is of course much faster than linearly working through all the other parts of the world. this origin is also cached, but that means that when the algorithm starts, actually it means that the origin is always the center of the cached area. That's how it's easy to explain. That's the easier way to explain it, I would say. And the origin is cached, so when the algorithm starts, it will be of course in the middle of the cached area, and you can move the origin, but the cached area will stay the same. So despite you are moving, the things that you are caching is not moving with you together automatically yet. But when the origin, like the real one, not the cached, but the real current, like the camera, the thing that you are moving and want to snap, or the player, when it moves in act, that it leaves the keep area, that is also stationary, then everything is recalculated. That's the point when everything is recalculated. And just a remark, this reuses the HeavyOpCheck already. Like we just have one thing as a building block, and this is the second, that this already reuses the first one. And of course it also uses asynchronicity to update caches. As a drawing, I think this makes it simpler. You have this big cached area, you have a smaller keep area, and the blue circle in the very middle shows when the origin, for example, the camera or the thing that you are moving into mouse, was when we started this caching. And this little purple, I hope it's maybe visible, but it's written that it's called origin. This little other circle means that where we are now, and you can see we are still in the keep area. So when we are operating, we only consider objects that in the cached area, so only those red dots, and everything outside of it is not at all considered. Whatever you are calculating, if it's being collisions, snapping, mergers, whatever. Okay, and if you would move the origin just a little bit more lower, so it leaves the keep area, of course then the cache recalculation needs to happen. And I already said that this will be asynchronous, so it will be not immediate, just we are hoping that you cannot go as far to even leave the cache area also, because we expect the origin to move like in increments, in small increments. And when I say that these things are really well documented, just look at this. Even the source code has this graphical comment at the same place. Of course, and we use the code from the previous thing, so we get a badge for it. I just give these badges because we should get used to reusing your code. Okay. So how you are using this? Like, okay, I told you where it is, and you have this constructor. You provide an origin. It can be of any type. So this is a generic with generic O. You tell the keep area size, which is just a number. You say a cached area size, which is also just a number. Of course, for any kind of sensible operation, this should be bigger than the keep area. It's documented above this, just I cut that off. Now, you also need to provide the distance function, like how to calculate a distance as a number from the origin from any other elements that you are having in this cache. The elements are also generic, so they are having the type T, and the origin is having the type O, so it can be anything. Literally, it's a really general algorithm. You also have this O distance function, like the origin from the cached origin, how far it is. You also can describe that. You also provide a function to get all the elements in the whole world, because for updating the cache, that's needed. Of course, you cannot spare that. There must be a way to know this. So there is a function to get all the elements. And actually, there is a very interesting thing here, is that you get a parameter for this. You provide a function or a lambda here, but for that function or lambda, you get the parameter of the current origin at the time of the getting from the cache. So it's updating the cache. It's really interesting why you need the origin. So logically, you don't need it. Yes, you just need to say all the elements in the world. But by saying the origin as a parameter, you can actually build recursive multi-level data structures out of this very simple one, if you want to do so. And those are the only things that you need to say, and you will have your temporal space cache. There are also some optional parameters. I was not talking about this before, but you can see that there is a timeout in milliseconds, which is defaulted to -1, which is like there is no timer. So you can put a timeout and you say that, okay, after this many milliseconds, the cache should be updated, whatever, because yeah, it's just needed. You also can say that, okay, this should be automatically updated, the cache should automatically update, or in the background while you are calling this. This is designed to be called in every frame actually, so but there is bookkeeping and everything automatically happening, so that's the default. But you can say false here and you need to call the updates by hand. That's a thing if you really want to do that. I had to do that in some really specific use case, so the parameter is here, but I doubt you will need it. You can also tell if you want to asynchronously update or you want to wait for the update. That's a thing. And also you can tell if you want to build the cache on construction or you want to lazy build the cache on the first use. And yeah, maybe you want to do that. Lazy data structures is a thing, so why not put it here? Okay, so how you use it after you have created it? You just have this cache get operation, you put where your origin currently is, and it gives you the temporal space cache result. Actually, the result is, yeah, it says see comments of the type for better understanding what's in the result. But for the simplest use cases, the result just contains the elements that are in the cache. Some features, of course, it's really generic. You provide how to get all the elements, support automatic everything bookkeeping in the background, supports moving the origin. You can see manual updates are also possible. I will not talk about that, but it's very well documented in the source code. And this is actually a little bit more interesting, the result that you get back. It doesn't just tell you the cached things, but also notifies you if you have left the keep area. So maybe you can slow your motion, you can enable fog so the camera is not looking so far that it maybe sees some buggy area or something. You can do something like this. And of course, the result also contains the previously cached data when a cache update happens. Because a cache update, of course, it might be prepared in the background, but when the real update happens, that's always when you get from the cache. So, actually, there is a point when we know the previous cache and the new cache together, and why you want to know this. I hope you don't. I really advise you to not need to know this. But for example, I have one algorithm where I use this as a building block where I do stateful things. I really advise against doing stateful things, but sometimes it's just faster. So if I do stateful things on some cache data, I don't know, paint really some dots red on that image that we have previously seen. When the cache moves, we might forget about them, and you can write your own bookkeeping if you want, but it was just faster to add it here, and actually I figured that, yeah, many people want to need that. Oh, and last but not least, you can stash and unstash the results. That means if you stash the results, the cache will look like empty until you are unstashing it. This is also useful for some upper level algorithms. So there are some caveats also. So I guess you figured that this is mostly useful for stationary objects. for static geometry and only your origin is moving with it. Of course, you can get away with the timeouts and big enag areas with moving objects, but you should be knowing what you are getting yourself into. So expect a lot of fine-tuning if you do that. It's possible, just I wanted to mention that you should expect fine-tuning if your targets are moving. It's used in a lot of things, in extraction for example, but also just for imagine the example I have already told you, this snapping example. So you want to snap to something and you have a big word and a lot of things to snap, and you only want to consider always the local vicinity to snap to. That's much faster, and this will work very extremely fast in practice. So I hope this was useful. It was a little bit more complex than the previous one, so let's go and just talk about some minor things for now, so that there is space for this to get calmed down in your mind. So I'll just talk about some geometric interfaces. Interfaces in this language, the TypeScript, they just pattern match, so it's also a form of generic programming in a way. If you have the properties of the interface or functionality as an interface, everything can be called in that function. We are having this i.2D, 3D, it's just x, y, and z coordinates, so a lot of algorithms expect just these. This is basically just telling that a lot of these algorithms are very generic. You can see the previous one was even more generic. But also there are like 0.2D and 0.3D which have these very simple operations like Manhattan distances and all little algorithms for these like classes. And the thing is that these are not tied to vector3 or some engine related things, but any class that has x, y, and z coordinates, or just x, y, and so on, these operations will work for it. So it's a little bit more generic, and that's really not much. But what is maybe a little bit more interesting is that I just want to mention there is also code for polar point 2D, like polar coordinate handling. That's just polar coordinates, like rotation and length of the vector. That's how you represent polar coordinates. But what is also a little bit more interesting is polar section, which is what section is with Cartesian coordinates. You also can have that with polar coordinates, and there is this polar section. It's really interesting building block for a lot of algorithms. For example, when you consider field of views and such kind of things. So it's interesting to know about. And there is this extended polar section that I use in some algorithms as a building block, because and that's just extended in that way that it has the Cartesian coordinates of the endpoints, because some algorithms just needed it, so it's there. Yeah. But there are also some function interfaces, and TypeScript interfaces can describe functions, not just classes. So lambdas that you give enough parameters or literary functions. And a simple example is just a comparator. But what we are using, and you see in many cases through this talk, is called a numberizer. And what a numberizer is how to understand a type as a number. Let it be any kind of type. Let it be Santa Claus, type Santa Claus. How to understand Santa Claus as a number. Maybe you want to understand the numberized Santa Claus as the number of reindeers towing the little thing that the Santa Claus is sitting inside. The sled, that's the word. Sled or sled. So yeah, everything can be numberized. It just depends on creativity. And it gives a genericity for a lot of algorithms if you give in objects and tell how to numberize them. So this is a very good and good building block. This is how they look. You all know this. And just move on. Move into Smallgorithms. So these were also small minor things, but there are other algorithms which are not this minor, but I have no place for them. Like they are so small that they end up just in this random place called Smallgorithm. So what is it? It's like geometries again. But I hope not, because hopefully it doesn't grow that big, or maybe it will, but it will be still usable, as geometries is also usable. So the idea is that smaller algorithms that didn't deserve their very own place, and I tell you where this is, and some basic algorithms, little algorithms of values and such, like if something is strictly opposite signed, like only plus and minus, but zero is maybe not playing here, so it's documented what it's doing. Is between interval. A lot of interval handling in one dimension is working, of course. Or do two intervals overlap? And this is handling when one interval is completely in the other way around, when they are separate, when one is having infinite widths or something, all kinds of edge cases, and it's reasonable fast and everything. So it just deserves a space, and I didn't want to put this in geometries. And elementary algorithms like minimum maximum search, like this is something I really usually use as a building block in many algorithms, that I want to search for both the minimum and maximum values. And you can see, oh, we are getting the code reuse badge again, because we are using the numberizer here. You just present the points, like some things, an array of some things. You tell how to numberize it, that's the code reuse. And this is getting you the minimum and maximum values according to that numberizer. How neat is it? Actually, of course, you can always write out the loop for this, but yeah, I started to do that and extracted this function because, yeah. And other simple algorithms is also here, like deduplications. An array having duplicates, you don't want the duplicates with a sorter or a set. But usually you do this with a set because, you know, inserting in the hash is constant time, it's big O1. So yeah, why don't you do it with a set? That's if you have n elements, you want to duplicate it, just insert into the set and grab it back into the array, and you are fine. And it's linear time, isn't it? Why you want to do it with sorter? Because with sorter, despite the sorting algorithm is big O n log n, for very small values, it can do it in one place, because what you only want to do is that you sort the array. When you sorted the array, the duplications will be after each other, of course. Very fine, very nice, and you can remove the duplications. And of course, by presenting the sorter, you can also make it so that this is true what I say. And also this is like fast for very few elements, but you can see that it all depends on the sort, because this is linear except for sorting. And if we would be able to sort as fast as linear time, this would be actually outperforming the set solution for very huge data again. And this is how we get to another topic, which is these all kinds of heap things. And first, to a recap, what is a heap? Basically, it's a priority queue. If you only look at the interface, it's not completely sorted. It's not a completely sorted data set, but you can always pop the biggest or smallest from them. Like not chain. You cannot choose. You pick the biggest and pick the smallest and pick. You can actually construct a heap like that, but maybe not. No, I don't. Let's say I didn't say that. So you can either always pick the biggest or the smallest, depending if it's a min or max heap. Okay. So you can also add new elements in the meantime. So this is not a static data structure. So it's not like you sort something and the biggest is here and the smallest is there. But you can always add in elements, and it's a priority queue. You know what a priority queue is. You push 20, 6, and 42, and if you get back, unrelated to the order, it will say 6 if it's a min heap. Okay, so that's the conceptualize. And of course, the by the book solution is binary heap. This is implemented with binary tree. There is only 2 rules. The parent is always smaller for the min heap or bigger for the max than the child, and the depth of the tree must be of the smallest size always. It's well-known algorithm or data structure actually. It's having linear creation time from an n-element array, big O log n pop and push time, and constant peak time. Peak is like just looking at what is the maximum without taking it away. Of course, that should be constant. So you see where here. So we actually implemented this in the code base. It's in the bin heap place. And if you are not familiar with this is how it looks if you conceptualize it. As you can see, for every element, the parent is bigger because here it's a max heap. But other than that, there is not much ordering to this. And what is also good to know, if you push something in it, for example 4, the 4 cannot end up in below the 6 or the 5 here, despite that keeps the rule 1, because that's making the tree too deep. So first we need to fill every line of the tree and go on and on and on. That's how it works. I don't go into details because this is a well-known data structure, but it's implemented for us. You should know how to use it because it's there. It's also worth to mention heap sort, which is also a known algorithm. Heaps are not completely sorted as I told, but you can create a heap from an array in linear time, then keep grabbing from it the minimum or maximum element depending on what kind of heap you are doing, and voila, you have sorted with using a heap. This is not magic because sorting happens in big O n log n time, like merge sort and all kinds of other sorts. Of course, it can be done in place. Actually, we sometimes don't do it in place. That's how it is. So, an idea comes up in geometry applications and 3D graphics and so on. Points are usually quite randomly distributed when we are interested in some points. Sorry. So we can maybe do some kind of trick that hashing and bucket sorts are doing in their data. Yeah, or actually I should have said geometry sorts that way. Prenex turbo sorts. I was working a lot in research in that area. So the goal magic here, the magic goal. This goal is sounding magical. Is amortized constant push and pop times, while keeping linear creation time. And if you put together that two, when we are using that for heap sort, we are basically sorting data. We are sorting data in amortized linear runtime. And that might surprise some of you, because some of you might have heard that it's proven that you cannot sort data faster than big O n log n, but that's not true, because what has been proven that you cannot sort data using comparison sorts in that time. So it's well known that you can sort faster in some cases. And what this amortized means, you can look it up for the exact definition, but for us, just say that in regular use cases with regular distributions. So yeah. So for us, it just means in practice it has linear runtime. Okay, how we can invent this? Think about polar coordinates in for a while. Let's say we want to put polar coordinates into a heap, and polar coordinates are like in degrees from 0 to 360 degrees. We can just use a regular binary heap and of course a modulus operation or something and some trickery. Or we can think like the following. And this might give you an idea. What you see here, actually the numbering should be different, because I would say 1, 2, 3 from the, I don't know, never mind. It doesn't count. But what you see here is that we created slices. he imagines slices around the origin. You see this is one of the polar coordinates here, this little vector. It falls into the slice 1. And we realize, why don't we just put a smaller heap for each of these slices? Those smaller heaps need to operate on far more less like number of elements, so they will be faster, because the sum of those small operations are smaller than putting everything into one big heap, if you think about it. If you think about it, the subheaps have m elements, which is the big n element that we have the whole element number, divided by the slice number. If slice number is big enough, this m is tiny. So just so that you can imagine, it's maybe like 1 or 5. Maybe only 5 elements are getting into the same heap here this way, even if you have thousands. Of course, we need some bookkeeping. Actually, what we need to do is it's very simple. We can, according to the numberizer, calculate what heap we are putting this thing inside, what slice. We can call it bucket also for bucket sorting. What bucket or slice we need to push inside, and while pushing the data, we can always do a minimum search if we are building a minimum heap, so that we know from what heap we should pop. And actually there is a little bit more bookkeeping, but I guess that's enough for you to get the idea. And we get amortized constant insertion time. It just all depends how you put this up. So how we are implementing this, we just say prenext turbo heap. Well, let's implement iHeap with this. Of course, it's not that simple, but yeah, that's where it is. And there is this interesting part to it, an interesting concept called isubheap creator, which is also a function interface, and it gets a comparator on the numberizer, and it creates the small heaps. So when you are creating this prenext turbo heap, you can actually tell what the small heaps should be. By default, as you can see, there is the default parameter, it's the last default parameter. By default, it's the binary heap. So the default use case, you just say the numberizer, like how to understand the things that I push into this heap as a number. We say the top of the domain, like 360 in our example, and this is a circular domain. We say the bucket span, not the count of the buckets, but the size of the bucket. So, for example, if we keep to the angles that we have been talking so far, from 0 to 16 angle degrees, they will all fall into the first bucket or slice. From 16 to 32, they will fall into the second, and so on and so on. And the bucket number you can calculate. And and this span should be like power of 2 for better performance. It depends on the JIT compiler if it optimizes it out, but let's at least make it power of 2 so it has a chance to optimize it out. Reverse, what reverse mean? It's very simple. If you want to use it as a max heap, you just reverse, because this is about min heaps. And you can say what to use as the little heaps. Like you have this function interface, you see it creates a binary heap with the comparator. But you can, with this, you can actually do again a multi-level structure and use, maybe you just make 4 parts to the big circle, and every 4 has a turbo heap in it. So that might work. Actually, this is not for degrees, but when you are having a lot of range, then you might need to do that for multiple levels, even maybe 3 levels. But for most use cases, and that's why it's the default, for most use cases, just using binary heap for the small ones and a reasonable big number for buckets, it will already like, you will feel as if it's literally linear time sorting, or actually heap usage, not just sorting. And we reuse the code again, so we get the badge. Yeah. There is this other static function, which is helper function, which guesses the bucket span, the number of buckets, for if you have values between this and that domain. Usually, as you can see here, there is only domain top, so everything is from 0 to this domain top, from 0 to 360 or something, so there is only positive numbers. But here there you can put in negative numbers and calculate the results, because of course you can say 0 for the bottom, but I just wanted to have this function in that way that you call it earlier. You will see why. So this is indeed magic, because it's usable for it will feel like linear time sorting. It's really scalable for heap operations also. Actually, I use this for heap first, not for sorting. I really had to have a heap where I can always pick the smallest, and I can also put back, like I pick something, I try to process and I cannot process, I put it back with some added values. So that's how I use this. So it was indeed a heap for first use, but of course you can use it for very fast sorting. And why not? It's there. It's also a recursive data structure. You can see that you can make as many layers as you want. And yeah, it's really generic because of numberizer. But there are drawbacks, because you need to know the domain in advance. You cannot have this for, let's say, user can enter any big integer and it will work, because then it will not. Like, unless, of course, you know when it stops entering and it will become an array, you can maybe search for memax search and start the domain, but otherwise, if you don't do and you do it in online algorithm way, then you cannot do it. And of course, the regular heap can do it. And also this domain is circular and there are only non-negative numbers. So that's a little bit hindrance, but you can usually transform your data so you can circumvent these drawbacks. So fine-tunings, power of two buckets, when I mentioned that, there are sensible defaults, but you can exchange a heap. I already mentioned that you can reuse the memax search to transform your domain into the 0 to something. Why? And also the negative numbers is very easy to handle. Just imagine that you have a domain from -5 to 10. Like everything, maybe in an array. You want to sort an array with the heap sort like this, and just configure the heap so that it works. So you know that your values will be between -5 and 10. What you do, you maybe don't know this, but you do a minimum maximum search and get these values. That's the minimum and maximum. That's fine, you know your range, but then it's like not from 0 to something. You just add the value so that it's 0. So it becomes from 0 to 15. That's all. It's really simple. By adding and subtracting, you can transform it. And then, of course, as I mentioned before, you can play with bucket sizes, recursive data structures, and fine-tuning the number of things. So yeah, you can play with those as far as you want, and you end up with some usable solution. For your use case, which is fast enough, even if you have immensely many elements, big range, you can parameterize it, but the default parameters will work. But this looks cumbersome, isn't it? Like, if all you want is just a linear time sorting or some very fast sorting or scalable sorting, this is cumbersome to do. Unless when we are kind to you, because we have heap sort. We implemented heap sort, and it's plug and play, scalable, and by default linear time sorting. It automatically calculates the minimum maximum domain. There is sensible default parameters. It needs just a numberizer and an array to sort. And of course, if I guess you have realized at this point that this is not just for polar coordinates and circular data, but all kinds of data where you know the domain. And when you have an array, because the minimum maximum search, you always know the domain. And we again reuse the code of the min-max search. Haha. So we have a very fast sorting algorithm in practice. So the brackets you can now imagine not as a circle, just like here. There are 6 brackets, little heaps, depending on where the value is in that range, it will be one of these brackets, so that's how it is. Okay, so this is the function that you need to call, like heap sort dot sort. And as I mentioned, you just put, say what's the elements, how you numberize the elements. It's completely generic. You can also tell what heap to use for the sorting. And for this sorter heap creator, you get the domain bottom and domain top. And of course, it automatically, by default, the default parameter shows how to do the transformation that I mentioned. You can see that the numberizer uses a different, like after putting the origin to the 0, and now it will say numbers like that, and everything will just work. And it will also use this guessing bracket span for, and that's why we use it like this. So I just was lazy to not do the subtraction here, and that's it. You don't need to add this heap creator only if you want to fine tune this. And you can also, okay, maybe you want to fine tune this and you have only a few amounts of elements, you know that, and you want to use binary heap for whatever reason. And you figure, hey, binary heaps doesn't need this domain bottom and domain top calculated. Hey, that's like a minimum maximum search. It's a linear operation that is just overhead for me. You can even say that I don't want to calculate the domain. You say false here, and the dom bottom and dom top in the parameters will be just chunk. So you can, if you use a normal heap like a binary heap, you don't need those. So that's all. And there is one thing that we did not mention before. If we just do the minimum maximum search, let's go back to our example from -5 to 10. There is an element that is 10, and if we want to sort that array, it should not be equal to -5, because that's bad. That's only true when we are having a circular representation, like actually literally like angles. So that's bad. And how we should avoid that? Because this works on circular data, and the simplest thing to avoid it is to increment the value a little bit. The domain top should be incremented by this delta value in the bottom that is having a default parameter, which work for pretty much all use cases. But actually, when fine-tuning, maybe you know that you are only using integers, you should set this to 1, or maybe you indeed using circular data and you want to set this to 0 and parameterize everything that way. So it's possible, but it's least possibly useful for most of the people, so this is the last parameter. And we reused a lot of code again. I hope it becomes a habit for others too. Even more. Yeah, I guess that's already a habit for everyone. So, binary and turbo heaps, final thoughts. You can say, hey, but a measure binary heap or just array.sort is faster. What's the point? Like, okay, this is not C++ with zero cost abstractions, I am set for that. And for small arrays, usually simple solutions nearly always faster, but it's actually not always the case here, because if the data is very much spread around, you only have a few data, like maybe 3, let's say 3, but they are so spread, no one is happening to be falling to the same bucket, then all bucket sorts, or not bucket sorts, or heaps, are just having one element. It's the simplest case, it's literally constant time, so it's not just amortized constant, it's literally constant. So if you're having few elements, but they are really spread, then this solution is still faster than the naive ones usually. I expect, yeah, it should be faster in C++, maybe not here, but it's at least measurably the same. Sometimes I measured it faster still. Anyways, the goal was not to beat the algorithm in every possible number of elements, but scalability. So it might be a bit slower for a few values, but it scales linearly. So, you know, actually, if you are having an operation only of few elements, unless you do it every many times, really many times in a tight loop, it will just run fine anyways, so it's not a big deal anyways. But if you are having a huge number of elements, this will scale well, and you will not bog down the performance of your application, and the naive algorithm would do that. So, and even if you really want to nitpick in these kind of things, you can put an if condition, and if it's below this many elements, it will just do the naive thing or whatever. And maybe you say, oh, but this looks complex to me, I just want to use array.sort and binary heap and everything. No, it's not complex. I just mentioned everything so that you know about the parameterization, but actually I don't expect you to remember all of that deeply. I just expect you to know that you can parameterize, and of course there will be this video for you, and you can look back how to do it. But no, it's not that complex. It's usually very simple. It's this simple. This is taken from real world code, just as an example. Only the first line is meaningful here. The second is just there so that you see that it's from real world code. You want sorted elements. It's from type T. You can say integers or points3D or something, but here I use T because this is from a generic code anyways already. So where I use this also in the generic. And you say heap sort.sort, the type you are sorting, the non-sorted elements, and how you numberize it. And you can put a lambda here, but I have a function. So that's all. And you get sorted elements in very fast time, scalable, everything. I hope you use it. So I hope you find this usable. This was again a little bit more deep dive. Of course, the how you use it is boiled down to very simple, but now I want to go back to some minor things, lay back a little bit, that you compose in your mind what you have heard. So minor things again, just random number generators. Is good to know that they are in the code base, but you might ask why on earth you want random number generators when the language is having them? Because currently you cannot, at least to my knowledge, compatibly seed this random number generator. And that's really a big pain in the ass. Why? Because you just sometimes want to get the same results. You want to randomize a lot of data, like a big point cloud or something, maybe for a unit test, that's the real use case, or speed measurements or something, and you want to seed it. And if you are not able to seed it, then you are not comparing apples to apples when you are making changes and optimizing or fine-tuning something like the default parameters. So I needed it for that. So currently there is only one because I did not had any need for something fancy and big. I just use Mulberry 32. I took this implementation, and it's where I just say where it is in PRNGs. So it's good to know about that. It's also good to know about, and this is more of a building block, is index point 3D. What it is, it's just an I point 3D, so an X, Y, Z, and also it has an I. And what is I is, it's an index. So works everywhere when I point 3D does. All algorithms accept this and give back the reference for this and everything. But you have this added information of the index, and you can encode interesting things in it, like where this data was in the original array before I sorted it, or where this data was in my original arrays before I put it in buckets and stuff like that. So it's a really useful building block. Because various operations might reorder, group, bucket, whatever your things, and you might want to correspond them to the originals. Good luck corresponding them if there are multiple ones very close and floating point numbers. You can try to make, if it's smaller than this data, I hope that it's the same, but it will be not the same. So don't go down in that rabbit hole. You have this index points 3D, very good building block, usable for a lot of things. Another use case, if you maybe already have an index, like you have some point, for example, you just have an array of points, but you know that this point came from an object in this array with this index, and you just store that. You already know the information, you just want to, again, correspond it back. Who had this point? Yeah, that's, or maybe an index buffer on a lower level. Yeah, it's written here. Or maybe you are having an index buffer, like a indexed rendering. You already have indices. You want to keep them for some reason, and you are having them right now. So I wrote where it is. I will not read it up. And it's very simple. As you can see, there is a y coordinate, and you can also create it from I points 3D. So actually, you can create it from really something that has an I point interface. I hope that was simple, because now we go back to the deep dive with proximity groups. Oh, I just moved myself a little bit because the fancy thing in the background. Okay. Okay, so the idea. Take a bunch of objects. Let's forget the 3D coordinates because that's a lie. It's just a bunch of objects. And a numberizer. And create groupings based on proximity. Wow, it's like, up to this point it sounds like bullshit because that's what the name implies anyways. So what is a proximity group? I just explain it by how to create it. That's the easiest way. So let's take the first object of this array, of this heap of objects, of whatever that you are coming from, the objects. And the first object defines the left end of this group, the first group. It's a defining element. A defining element. Further objects that you are grabbing belong to the same group unless the distance from the defining first element is bigger than D. Then a new group will be opening up. And the new one will be the defining element for that group, of course. So I think it's best to show this in examples. Let's say we have point 3Ds, but we only numberize them with the x coordinate. You don't see the depth here, but it doesn't care too much. So you see the x is the x in the viewport here in the presentation also. You can also see the d parameter. I just draw it, and as you can see, it became 3 proximity groups with these parameters, and the red dots are the points from, I don't know, front view. So there is this blue proximity group, then there is this hole. This is really good to pay attention for. So this is not space partitioning or something like that. There can be holes. This is a sparse data structure. Then of course the next defining element was too far from the beginning one, that this one, the left one from the blue and the left one from the yellow is what it was compared if it's further than D. And of course then a bunch of objects fell into this proximity group, and then other proximity group opens because it's again too far away from the first one, and it also has some objects. Okay, the drawing is not perfect, I draw it by hand, so yeah, that's how it is. But the key remark here is that there can be holes. And actually, I did lie a little bit because the only way we can get this result if we are sorting the points beforehand. Now you know that we can sort in linear time, like, yeah, in usual and practical use cases. That's fine. But other than that, the algorithm, if the data is already sorted, the algorithm runs in linear time already. But how this looks depends very much on how the numberizer is. And the other example is this circular. So its points, okay, you can imagine two-dimensional points. I don't know why I say points really here. But maybe two-dimensional points, and they are numberized from the distance of the origin. And as you can see, you get these target-like structures with this. With proximity groups like the different colors. So x2 point, which is, I don't know, it's in the red, it's in the red group. It's also in the same group, and the x8, despite the x1 in the yellow near the bullseye, it's closer to x2, like by normal distance, but by this numberizer, of course, they fall into the same group. So it all depends on the numberizer. Some call this numberizer a single-valued kernel, and you might find a lot of kernel tricks. That's something that you might look up, because a lot of kernel tricks actually help in a lot of algorithms, but I just call it numberizer because that's what it is, and it makes more comprehensible to use. Okay, where this is, it's in UTS/performance/proximity group. And because you expect sorted data and a lot of things, you usually don't want to just call the constructor directly, because TypeScript can only have one single constructor. So we have this helper function, this static function, create groupings. And as you can see, you give in some non-sorted elements, because it doesn't need expect sorted elements. You give in some data size. Of course, that's the D. You give in how to numberize them, and that's only the mandatory parameters. And this will create the groupings. And by default, it will sort the elements. So the groupings will be as on the image. If you don't sort the elements, actually the groupings can overlap each other. And that's, I don't know. So here we sort the elements. And avoid single element group creation is a parameter that you would rarely use, but maybe you want to do some calculations on elements that fell into the same group. And if there is only one element, there is no point in calculating anything, because I don't know. So you can do this, but as you can see, as we further go down, more rare and more rare, you need to use those parameters and just rely on the defaults. And as you can see, say what heap to use for heap sort, and by default it uses the well-known Prenex Turbo Heap with the well-known parameterization from heap sorting. But you can do it with whatever you want for fine-tuning. I don't think you would in most cases, but it's there. What it gives back is an array of proximity groups, and I guess that's really fine. So that is this. Oh, a lot of code got reused, like numberizer, Prenex Turbo Heap, yeah, and it's also very generic algorithm. So some properties. This works. You can see this works if the input is sorted, like it gives the image that have been on the picture. But we sort it unless told not to. On sorted input, the groupings is clearly, creating the groupings is linear time. So that's actually good. But if the input is not sorted, it depends on the sorting algorithm, but we have seen that we have this amortized linear time sorting algorithm, so it will be fast enough for scalability use cases. And by sensible difference, we are using that Turbo Heaps linear sorting. Actually, if you are not sorting the data, because you can ask not to sort and still run this, but know what you're doing, I don't know what it will lead to. It will have a lot of overlaps, and they can overlap. That happens when no sorting is done, you know. When no sorting is done, you will get the first defining element, you will get elements into this group as far as the D goes, as far as it can happen, but then some element, because it's not sorted, very far away from will be coming, and you get a new group there. You have some elements in the vicinity, so you go in the group, and then you jump back. Actually, this is programmed, so you will not crash on anything, but you can jump back from that because the absolute value is different, and it's too far away from, but it's more far away than D. So it can grow both directions actually in this unsorted way. The proximity groups can grow both directions. It's really behaving a little bit weird. And if you jump back, you can have overlapping groups. Or maybe even the same. That's really rare. I cannot imagine that happening in real use cases, but of course it will always happen if you try it enough times. So I don't know what. Actually, that's a yeah. Actually, that's a really cool building block. Yeah, because if I think about it now, I was not thinking. Yeah. It's really funny. Sorry for interrupting this presentation, but if you think about it like that, you can just put in the proximity groups in an unsorted way. It will grow in both directions. Yeah, and if you have nearly sorted data with like data that are like clustered, so all your data is clustered into bigger clusters, then this will have like smaller clusters. It will become groups automatically, and you have overlapping groups. Then you can sort the groups themselves because the groups are actually having the end and beginning of them. Yeah, then you can sort them and use the merge operation from the merge sorting and step through them with an elementary processing algorithm, and you actually get a very fast sorting algorithm out of this. So, okay, I was not planning to do this, but actually I have invented a sorting algorithm by using these building blocks right in this presentation. So I hope this is... sorry, I had to not stop the video because I might forget this. It's already, I don't know what the date is, but okay, this was not working. This is also not working. But the date is Okay, it's nearly half past midnight. So yeah, it's not in company time in any means, like that company time that I sell to other companies. So if this is a sensible algorithm and I want to really keep it because it's maybe very faster, I don't know, then I can of course now sensibly do so, and I will not forget it. So I don't want it to stop this recording just for the sake I should not forget this algorithm. But this is also a very good example. If you have building blocks, you know, you just talk about them, use them, think about them, and new algorithms pop up constantly, and they are great. Ooh. So this is why you should think of reusing and building blocks in this sense also. Anyways, coming back to the presentation, sorry for this little misbehaving. Okay, so unlike partitioning, maybe that's where I was. No groups are created between foreign elements, so this is a sparse data structure. It's really, yeah. I will just come back. I will not think about that fancy sorting that we just invented right here. So you can actually ask. I know that this is capable of that, so that's how the sorting came in. You can ask if proximity groups overlap with others, and you can also ask if it overlaps with some delta. And what that means is that just imagine this picture here, in this case, and you can say that there is a hole between these two, but there is no hole between these two. Maybe there will be a very small one, I don't care. But the leftmost element in the green one and the rightmost element in the yellow one is clearly closer than D. And maybe you want algorithms when you want to consider elements that are closer than D in Cartesian coordinates. And those two need to be considered, despite they are in different groups. They need to be considered because they are on the sides of the groups. So actually there is a little query that tells if that overlap happened. So you say the D number and you say the other proximity group, and it tells you if there is an overlapping considered in that data. So this only returns false if it's not possible that any of your elements are closer than data, not even the ones on the edge. This is also really useful. You can mix neighbors of a grouping. And what mixing means is that after this mix operation, the group E, group I, in the result, we also contain the elements of group I-1 and I+1 before this operation. And actually this operation is written in a quasi-optimal way. I think it's pretty much optimal. So it happens in place, not calculating a new array from the previous. So it's a little bit tricky. Of course, even that would be linear when this is linear time, but it's a little bit faster linear time, how it's implemented. And of course, yeah, some of these things only work if you are really calculating Cartesian coordinates, but you know, these are building blocks. It's up to you how to use them. Okay. So another idea is subgroupings. So we might subgraph, not just graph, but creating subgraphs. First group your elements using one numberizer. Then group those groups, like the elements in these little groups, using a second numberizer. The biggest example is using perpendicular axes, like x and y. So first we numberize, first we use the numberizer on the x-axis and create groupings. That's what we already seen. This is the result. Then we numberize those groups according to the y-axis. And this is what we are getting. And I also go ahead a little bit here by that picture, because as you can see, this is not what I said. This is a little bit more than what I said by explaining this, because there is this D1 and D2, and you can see that D can be different actually for the different like coordinates. But what I said is to numberize the existing groups, like elements, vertically here. So why there is no cut between the blue and I don't know, nearly same blue here in the middle on the right side? Why there is no cut? Because the algorithm actually, yeah, here, the algorithm actually has this flag consider neighbors, and by default that's true. Why it's true? It's actually for the same thing that I mentioned before when I was telling the mixed neighbors. This is actually making mixed neighbors part of the subgrouping, because just imagine that there are these, I don't know, some elements that are very close to each other. Maybe they are not to be considered in the first numberizer, but now in the second one, you should see that these two should be like I'm talking on the two ones near the yellow and the green groups, edges. We should consider if those actually are numberized in the same group in the y direction too or not, because maybe they are so close that they should be. So unless we have been doing all kinds of coordinates, this should happen. This basically is a shortcut so that you do not need to mix neighbors. And actually this is faster than mixed neighbors, even faster than that, if you do this. And of course, how you do this, you can see that by mandatory parameters, you just say the previous result, the proximity group array that you have got from the create groupings. You say the delta for the subgroups. You say how to numberize this in other access or something, and that's all. That's all. That's the default parameterization. It will work for most cases. It will be fast for most cases and very good for most cases. And what these other parameters is that if you want to consider neighbors, because then it will mix them automatically, that's maybe something you might not want. So it's the first default parameter, so that you can easily set it to false. You can also tell if you want to sort the elements or not. Maybe the most use case here, I don't think I can invent another algorithm on the fly in this presentation right here, but the most use case for not sorting the elements would be if you know it's already sorted according to that direction or something, because of why not? Maybe your input data is like that. So you can also ask, and this is true by default, to avoid single elements, no neighbor group cache. I want to stop here a little bit because this is fancy. What is single elements, no neighbor groups? I go back to this picture. Let's imagine that on the left side of the picture where there are two dots. Let's imagine there is only one, and you want to calculate some collision or something, like something based on proximity actually, because this is all about proximity. Cartesian proximity. It will be alone completely. It's not at all possible that anything would be in proximity in any kind of direction. If there is only one element, if just imagine if there would be two elements but with the same but they would only differ in the same z coordinate. There would be two dots in here just on the same position. So if there is only one dot and it's already separable so much with every direction, then for most calculations, when we are using this proximity group as a building block for calculations, we can just ignore this, throw it away, and everything will be faster. So it works setting this as true, so that's how the building block is. And of course, as usual, you can tell what heap to use, because maybe you know that there are very few elements and the simple binary heap is much faster than this, I don't know, other. A lot of code used, we get a batch for that. Yeah, I'm a little bit tiring, but yeah. So final thoughts on proximity groups. You can see it's mostly a building block, not much used on its own, but there are a few cases when actually on its own it's used. In most cases it's a base for more complex algorithms. And actually now there will be an algorithm based on this, and I already not fully explained but hinted a sorting algorithm that can be made by this. So yeah, that's fine. Okay, I would need to think about that more and fine-tune it more, but I think it's an idea worth at least investigating. And it came up just right now. Yeah, it's so funny. So anyway, sorry, coming back. So final thoughts, it's mostly a building block, runtimes, creating groups is amortized linear because of the sorting is, and if it's sorted, it's surely linear. Creating subgroups of those groups is still amortized linear to the original element number. That's some more of a thing. Just it has this 3 times like multiplier on it, and yeah, that is to be considered. And that multiplier happens because we duplicate data when we mix the neighbors together. And there are also various micro optimizations, like considering neighbors is faster than mixing, and we avoid groups that are surely lonely, and so on and so on. And yeah, but there is something here that I didn't mention, is that there can be duplications here, if because of mixing, but that's common sense. Okay, I hope this was useful. It's really a low-level building block, lower level than the before ones. So we are moving for a collision detection engine. Let's talk about the problem space and the idea. The problem is that, let's say we have n number of objects in 3D space. There is a size of D, like every object has this same size, or actually maybe they are different sizes, but you can say what's the maximum size, and it's still a sensible value. Like it's not like very huge versus very small. So it's more or less the same sizes, but there is a maximum to it. Then even then this can work. And the question is, what objects collide? That is, which is closer to which than D? And the second explanation is the better, because that's what we are searching for. It's not really collisions, because maybe you don't want collisions. Maybe you want merging, for example. No, what is that? Snapping. Yeah, you want snapping or merging, vertices merging, snapping to objects or something like that. And the key here is that we want all of this in one step. Like, we are not just moving one origin like in the TemporalSpaceCache, but maybe these are all moving, and also we are interested in all of the possible collisions. Like, if there are 2 circles here that are collide, we want to know that. If there are 5 circles here that are colliding each other, we want to know also that. And after one run, all of these collisions will be reported at once. So it's very good for simulations and all kinds of things. And I guess you'll see that it's a different algorithm than the before one. Okay. And where this is, so you can see that this is not just an idea, because this is like sdlib/src/utils/performance/CollisionEngine. And this is what we are talking about if you want to depict it. A lot of like spheres, and want to tell which is colliding with which. Okay, let's start with the naive approach, simple naive algorithm. You have n objects, you iterate over one of the n objects, like all of the n objects, and you just measure if you collide with all the others, isn't it? That's simple. And it's quadratic, simple and quadratic. And actually that's still not the best naive approach. There is a better naive approach when you are iterating from I with the I iteration variable. You don't need to always compare against all the others, just the n minus I number of others. Because if we are doing it in this order always, these two have been already checked. So that's a little trick, and that leads to a little bit better runtime than the literally square, because this is like n multiplied by n minus 1, and the whole is divided by 2. That's a well known old dirty trick, or actually elegant trick. And this is implemented. We have implemented it in CollisionEngine that slow naive collisions. And why the hell we are implementing? Because this is surely slow. You have 100 objects. This inner loop will nearly 10,000 times, or actually, of course, okay, 5,000 times it's we are running. That's a little bit big. If you have 10,000 objects, it's nearly, oh my god, it's 1,000,000 times or something the inner loop is running. So as you grow, it grows crazy, and it's not scalable. The reason why we implemented is threefold. This can be used in fancy algorithms as a building block. Yeah, code reuse. There will be badges for it. And the second is that we can test the fancy algorithms to something, because we know that this is good. This is really easy to check, really easy to get right. We can write unit tests against these. With the fancy algorithms, we can unit test against the results of these. So that's necessary at some sensible level. And the last reason is that actually this can be fast enough for small numbers. So yeah. Ideas. You can do space partitioning or other trickery like grids and octrees, and of course what we talked about before. Actually, in practice, dynamic octrees are quite complex. I have written one once. Of course, it can make the work, but it's complex. It's a complex thing, and a dirty algorithm. So mostly in practice, they use only grids in most of the time. TemporalSpaceCache might help, but it's not really dynamic, so you might need to play with the timeout values. Of course, it also can help if you just want to move one object, or you want to consider collisions with one object to all the others and faster than linear time. Then that's what I advise. Go with the TemporalSpaceCache. Maybe it will be better. Even with the moving objects, you add a big enough cache. That should work more or less. Or we can write a completely fancy new algorithm. And I wrote, but that's true. I have one in C++ and not here in this presentation, by the way. It's actually faster than this, a little bit better than this, more widely useful. But this happened first, what I will present, and this is in the source code base that you are familiar to. And mine is not in the source code base as far as it is now. And it's in a different language and everything. So, okay, those are good ideas, but proximity groups, hey, we are talking about proximity groups so far. Hey, isn't the proximity group is what we want? You are right. That's why we invented proximity groups actually. We can just reuse them, isn't it? So, we use proximity group. We group by x coordinates. That's linear time, amortized linear. We have talked about it, it's understandable, everything. Then mix the groupings, because of what I told you, that there will be these dots that are on the edges and very close to each other, so we need to mix the groupings, so neighbors ends not further than the mixed. And we can calculate collisions then naively per group. And actually, I have implemented another variant of the naive algorithm, and that's what the naive algorithm under the hood uses, that do the naive algorithm progressing. So if you call it multiple times with the same array, it will put the results into the same array. That's trickery. So that's actually a really good building block for all kinds of collision engine algorithms. So we can do that naively per group, and then there will be, of course, duplications in the result, and we can deduplicate it if you really want to use that. Or maybe the way we are using that is not even needing the duplication. We want to, I don't know, destroy some object. If it's colliding, then we don't need to deduplicate. We destroy, and there is this flag, and the object will be not there. We cannot destroy it twice. So yeah, maybe we want to deduplicate, maybe we don't. If we want to add some values to, I don't know, scores or something, or calculate something, we might need to duplicate. Okay, so this is more faster, clearly, more scalable, clearly. Hooray, isn't it? This is fine, but we can do better. Just imagine that this is what we are doing now. We are using the X dimension only, and there are a lot of unrelated points that we are still considering, because just imagine, these are not this small, these columns are endlessly big. They are infinitely big. A lot of points fall into that, and if it's really a lot of randomized points, like a big scene, a lot of things are literally uselessly considered. Why would we do that? Of course, this is what we do, this little animation, that we consider the neighbors, we will join them, and of course we used a lot of code from the proximity group. Hey, yeah. So now we can enhance this by using subgroupings. I guess you already screamed that. Why don't use scope groupings? It's like it's made for this, and you are right. That's how it's implemented, how it's invented. So proximity subgroupings to rescue. We should create groupings by X, then get that result and create subgroupings. Already say that we will mix the results. It will be very fast, and we should consider the X neighbors. Yeah, that flag is automatically true. Then we create groups with Z, with the Y neighbors considered, and in the end, we should not forget to mix the Z neighbors in our algorithm, because it's very easy to miss that out. I have did that, so that's why I added it here deliberately. And because of mixing, we have at most 9 times the n elements total in this data structure, like that is an upper bound. It will be, because of optimizations we are mentioning the proximity group, it will be a little bit less, maybe a lot less actually, but that's how it is. So we do again the multi-level thing, code reused, very nice. But does it worth it? Because like maybe the first is already fast enough, or maybe just other solutions are fast enough, because many duplications are introduced in the result, and either need to be deduplicated or we are running over them, and maybe our algorithm doesn't care, but it's still there as runtime. And here it's like 9 times the scalar, not 3 times like if you would just do in the one direction with mixing. And very scary nested loops look like in the source code that, oh, this is at least quadratic, or I don't know, exponential or something. But yes, it's worth it. Despite any scary loops in the code and how scary they will look, the total element number, we can have an upper bound on that, and it will be linear. It will be like, of course, amortized linear. There are worst cases when this is actually the worst case, yeah. And we will talk about that. And finally, we have already amortized linear time thing if we use Prenex Turbo Heaps. And in practice, I just measured that the Z level groupings, if we do X, Y, and Z, numberizer and groupings and subgroupings, in the smallest groups, the elements in one single group is so small, it's like 2, many times it's 0, sometimes it's 6, and not more. So it's very little, and we have tens of thousands of elements that we are working with, and these small values are popping up. So despite we are having these very scary nested loops, and here I again mentioned the mixed neighbors to be not forgotten, so that's actually why I put this image here. So even though this is part of the implementation, so you are not needing to do this, you just call CollisionEngine. But so it looks like very crazy deep. I don't know, this loop will take forever because there are 3 loops in each other, and there is a possibly, oh my god, a quadratic operation in the middle of the innermost loop. Oh my god, you might think that this is taking endless time, and actually this is amortized time linear. And just to this slide is just here so that you see that what the Z graphs is that we are running over. That is like proximity, a 3-dimensional array of proximity groups with various lengths. So it's like not a cube, but it's like a Quasimodo version of the cube, different sizes in each kind of columns and rows and everything. So yeah, and we of course make a loop on the on the previous 2-dimensional matrix and create this unholy thing. So yeah, it's fast. And what's the API for it? Because okay, we have implemented this actually fast CollisionEngine that is fast in practice, and despite scariness it will be fast, and I measure it to be fast. What's the API? Okay, so this is not the source code, this is not the solution that we are running. This is just the parameterization. This is the default parameters that you are calling. This looks scary, isn't it? Like this. Oh, this looks scary. What the hell? You don't want to work with this, isn't it? But actually, if you look more truly on this, what are the mandatory parameters? You just give in the points, like anything that pattern matches to the I point 3D, so it has x, y, and z coordinates, and it's fine. You just give an array of that, and you say the d, like what's the sizes, and everything else is not mandatory. It just works. That's the default parameterization. So let's see what we can work by changing the defaults. You can say the numberizers, and those are like just taking the x, y, and z coordinates for each time. That's a very sensible default. But maybe you know that you are having a 45 degrees plane that things are going on, and maybe the data is like that, so it's faster for you to do that. And the numberize like that, you can do it. That's a more use case. And if it's not, yeah, it's fine. Or maybe you want to calculate, you have three-dimensional points with z coordinates, but you want to only calculate the results on a plane because it's faster. You can say that, oh, I want z numberizer just returning 0. That's actually a very smart optimization. If you think that the collisions you only need to calculate on the xy plane or any other plane, to be honest. That's a thing actually. So, and what all other parameters are, there are only 3 more parameters, but because of the default values, they look quite big. So you can see the y heap creator, the second of these 3, I actually cut so that I can fit this image on the screen. Yeah, but it was more or less basically literally the same pretty much than the for the x heap creator, so I just cut it. Not literally, because it uses x numberizer and this used y numberizer, but other than that it was pretty much the same. So what these default parameters are for the x, for this x proximity grouping, I would say we would use this turbo heap, which is amortized linear time. I advise you to always use this because on the first level, on the x level, because then, yeah, and of course the x level should be the one that separates your data the most. So that's also why you can say the numberizer. And maybe you know that your data is really spread in one direction and not the others. So in the x heap, you should use the Prenex turbo heap because there will be endless amounts of data. It should work with the turbo heap because that gets the best. It should be always a Prenex turbo heap pretty much all the time. But you can parameterize it, but it's pretty much always like this. The Y heap creator, that's not that simple because depending on how many objects you have, usually it can be better to use a binary heap here, or maybe also because the spread, the spreading is also affecting the Prenex turbo heap well. So if your data is very well spread, you can use the Prenex turbo heap here as well. And for the last level, I already by the default I put binary heap because, as I told you, I measured that even with tens of thousands of elements when we are running this algorithm, these actually have the last level usually have like 0 to 5 and 6 times the number, not times, number of elements. So it's really small. Binary heap is really much faster. It can count as a constant in this amortized calculation. So this is the best for here. And you get the collision results. So it's easy to call, nothing to fear about. But the problem is that when you are just looking at the file, this is what the user sees, or the other programmer that wants to use it, and it will be scared away. So it will not use these turbo sorted collisions, despite it's actually, if you think about it, it's just 2 parameters that you need to set in the most cases. So I just made this little convenience function called collisions. So it's like CollisionEngine.collisions, and it only has 2 parameters, a nice description of what it does, and it just calls the turbo sorted collisions in the right way. And it's not only just here so that you can be more brave to use this and not scared away by that mess that you have seen. But also actually I made this so that if we came up with a better solution, for example, once I port over the solution that I have in C++ or something, maybe that will be the default one later. Or who knows, someone invents something very, very better, then that will be the default one. And the thing is that, yeah, this is always intended to call the default one that we think is the best for the generic use cases. So basically, every time you call a CollisionEngine, I advise you to call this one. The other is there so that you understand what you can fine-tune, or if you are finding yourself that, okay, this is not working how it's intended, it's not fast enough, you can think why. But this is much more, okay, I can rely on this, because this is much more I like it. Not like this, fearful, but this is more I like it. Okay, what is the result that you get? It's not just a simple array. It's actually, the result tells you if there might be duplicates or not. And also, I think there is a function to deduplicate it. I might not mention it on the slides, so I'm mentioning it here. So you can deduplicate the solution if you want. Yeah, of course. It also tells if it's normalized. In most cases, it will not. And the result also tells which collides with which objects collides with which. And this is an array. It's really simple. The fifth array element tells you what objects, what indices the fifth object have been collided with. So if the fifth array element has this other array with 2, 4, and 10 in it, then you know that the object 5 has been collided with 2, 6, and 10 numbered objects or indexed objects. It's that easy. And you get it for all kind of collisions that is happening. You can query all the objects, very simple to use. Nothing is needed, like you don't need to think much to use it. There are some operations also on a collision result. You can filter collisions. Like you calculated these collisions, but now you want to linearly go through this result, which might be big or not, but we wrote it out, so it already took the same big old time to go over it again. And you can filter some of them out, throw some of them out, because maybe you know some other conditions that you want to check for an extra, and it's not positional, but I don't know, these objects are marked as dead or removed, I don't know, something like that. Or these objects are marked as not taking part of this computation, or I don't know, anything like that. Anything that is not positional. You can throw them away. There is also possibility for normalization, and I would call there is also possibility for deduplication. And those are not the same. Deduplication is, it just ensures that one collision is reported only once. As I say, some algorithms doesn't need that, so by default it's not deduplicated. I think. Yes. And actually, some algorithms, of course, need it. And normalization is different. I just want to tell what normalization is. Normalization, you can say that there will be maybe in the future a lot of collision algorithms in this CollisionEngine. And already there is two, the naive and this turbo one. And for the unit test at least, and also for all kinds of future use cases, there needs to be a way to correspond the result of one engine to another. And these are calculating things differently. The order of the results will be different because these are not sets. For fast runtime and fast lookup times, these are just plain arrays. One might give you duplications, the other might not. So how you make this possible? And to make it possible to compare for equality, I had to come up with a term like how is a normal form of a collision result is. You can go deep dive into the code to see what it is. It's basically, yeah, it is very simple, but you can ask the collision result to normalize itself, so it's comparable to any kind of engine's result. That's really good. That's what I use for unit testing. So that's why I had to implement it, but it's also implemented in a fairly performant way. I think it's also amortized linear time, so that's pretty cool. And there are other operations like clone, equality. Equality uses this normalization, and there is row equality which doesn't use the normalization. So row equality only works if you are comparing results from the same engine. But if you are not using the same engine, you should use equality, and that will normalize for you. Okay, I think this is an example use case just from real life code again. So a snippet, you say you want a collision result, you call the CollisionEngine, and you want to know the collisions between these vertices with that tolerance. Here I am merging vertices, I'm not colliding, you can snap, collide, whatever you want to calculate. Or maybe you just want to calculate, I don't know, some fancy algorithms, or maybe heating, maybe you put down a fireplace and there are a lot of fires and a lot of furnitures, and you want to calculate how the heat affects some of the furnitures, but of course you only want to consider those that are in the vicinity of the fires. That can work. That's a calculation, that's not collision, but you can use the same algorithm for that. Or maybe you want to calculate, what is that, COVID simulation. You have a lot of circles, spots like seats on chairs, spots on a bed where humans can be, spots where humans are intended to stand up for a lot, like at the coffee machine maybe there is a spot where you usually stand a lot, and the door where there are choke points, and you can simulate and calculate if any time what is the collisions between all of them, so you can maybe draw lines between them or something in just one operation. It's very fast, it will work, it's linear time operation. Okay, so this is an example. I use it for merging vertices. Here I use the thing of the algorithm that because everything will be very much separated in my use case, except for those what I want to merge, and the tolerance is really small. This will be really fast, even for small number of elements. So I calculate the collision result, but unless this is not only position based, because there is a possibility for that, we will filter out collisions where then and only keep those where the normal vector is also the same to some tolerance and the UV coordinate is also the same. So this is basically the same time as running this. It's the same runtime. So if the collisions are very many, this will take long, but then we cannot do anything. But if the collisions are reasonably amounted, then this will be fast also. And you also get this collision result, collisions. This is an example. And that collisions is just an array, as I mentioned. If the fifth element of that is like 2 and 6, then the fifth object here, the fifth vertex is between tolerance with the 2 and 6 vertices. That's simple. And here it's after also the filtering. So great. Some properties, runtime, amortized linear, usually for your practical use cases. But worst case, why I say usually? Because worst case, this falls back quadratic. And it's very easy to see when everything collides with everything. You remember we return a two-dimensional array, and that array will be totally filled. Just filling that array will be quadratic. So it cannot be faster than that with this API. Of course, you can code a space partitioning and then it will be faster. So maybe that's why I say maybe there will be more collision engines, but this is the default one. So worst case is quadratic. But scalable and usable in practice, And when objects are well separated, and this is I mentioned before, far away in all axes and everything, this is usually faster even than the naive algorithm, even for small number of n simple sizes. It's interesting, but it's a good to know thing about this algorithm. So it's useful and reusable. Everything that fits like pattern matches to that interface, it can work on. Okay, what about reliability? Does it? Can you use it for reliable? Are there tests for it? Yes, it's well tested. You can actually run this test even from the console. There are unit tests, and even the speed was measured. Like, actually, I measured the speeds for the other things as well, but it was too far away in the past that I could not find the data anymore. I just measured it, then threw it away after the fine-tuning and parameterization. But here, speed was measured against the naive approach, and I wrote the test in it, so you can still test it because that's better. There is this test speed function, and you can say the number of elements, the range. The range means like what is the area that these elements are spawned into randomly. Because as you can see, both the Prenex Turbo Heap, it really works faster if everything is well separated. So the sort operations will be more linear. And also the CollisionEngine algorithm itself with the proximity groups, it's also faster if things are more separated. A lot of times it will optimize out completely for the lower stages. So even at the y coordinate separation, there will be a lot of the proximity groups from the x separation that will be thrown away. So it's actually very fast. It can be very faster than the naive for low number that are very much separated, and with numbers that are random, that's usually the case. So some measurements and final words. Random points in 30 to 30 to 30 cube. It's a little cube with a d of 5. So everything has a size of 5. This is the result. On the left you see the naive results. Naive algorithm. On the right is the more fancy turbo algorithm. And actually, yeah, if you look at this doesn't look such promising, isn't it? It's like for 100 elements, like a few elements. Actually, these are in milliseconds, so it's not that big of a deal. But it takes 1 millisecond for the naive and 7 for our solution on average. And that's not looking good, isn't it? That doesn't look good. It's 7 times slower. Okay, make it a bigger deal. So let it make it 1,000 elements. Now it's more like, yeah, we are in the same range, but the naive algorithm is still faster, like 1.2 or 1.5 times faster or something like that. Yeah, it's still faster. Let it be 10,000 elements, and you can see that the naive algorithm is still faster. It's getting crazy, isn't it? Because 10,000 elements, maybe you would never use that much. And in 50,000 elements, which is awfully lot, then finally, oh my god, yes, we at least managed to grab some honor, because in 50,000 elements, our algorithm is at least faster now. So great. But there is a problem with this. A 30 sort 30 multiplied by 30, like it's a very small cube, and these are spheres with the size of 5. Just imagine 100 spheres in that very small cube. It's already nearly everything is colliding with everything. So basically we are calculating the worst case. Okay, not the worst, like everything in one place, but yeah, it's actually worse than that, because then it will only create, if everything is in one place, we would only create in one proximity group. We will not calculate the overhead at all. But here we are calculating the overhead, yet we nearly end up the same result where everything is everything is colliding with everything. So this is literally the worst for our algorithm, and it still managed to get faster after a big amount of number of elements. So yeah, there is hope. just make the area bigger, like 3000 multiplied by 3000 multiplied by 3000. It's a very big cube, and we just keep the size the same. Of course, you can make the size smaller, like I did before with the merge vertices, or this is also possible to make the area, the word, the level, or whatever bigger, scene bigger. Now measure again. For 100 elements, we are already faster, and not a small amount. It's like nearly 5 times faster our algorithm for the small number of elements, because it's well separated. Oh, great! Yes, well done. But then we up our job and go up for 1,000 element, and it's not that good, because you see it's like 10 against 18, so we got to be slower. What? And there is a simple explanation to that. Here is when we started to have collisions at all. With very few elements, only the fast part was happening. The fastest part, all the micro optimizations, everything was thrown away because they were completely unknown in their proximity groups. So it was all fully fast because they were so far away randomly. Now it's that many are colliding, because you can see that the D is still 5. It's like 1,000 with the 5 size. There should be a lot of collisions in this range. So we got to be a little bit slower, but it's not a big deal because it's like less than 20 milliseconds for this 1,000 elements, so you can run it anytime without problems. Okay, go up for 5,000, and you have maybe already read ahead, and you see that now 77 milliseconds for the regular algorithm, and it's 24. It didn't marginally grow for ours. Okay, here we can start to see the scaling. Now go for 10,000, and you can see it's nearly 200 milliseconds nearly for the naive algorithm, and only 37 for ours. And if you go up to like 50,000, it will take 5 seconds to calculate for the naive algorithm. I know this because I have calculated it in a lot of vertices for test before, for the vertex merge. So it will take seconds, literally. And now our algorithm still takes only 200 something milliseconds. Okay, so it's like naive versus turbo. And the final words is that 50,000 points, you can use this algorithm, and even if you have 50,000 points, it will never stutter or lag, because unless you do this in every frame, because then this becomes a heavy operation, really heavy. It's still very good, and with the naive solution you would wait 5 seconds, which is not even acceptable even if it happens on a button press. So yeah, maybe you can make it async and a lot of code, but actually writing this algorithm is nearly simpler than making that asynchronous and handling asynchronicity in the background. And the other final word is that this is still not designed to be called every frame, because this is not stateful. You can see that all the proximity groups and everything is recalculated every time if you call it. So if you want to have it for every frame, it should be stateful. The algorithm that I have in C++ is actually supporting partial updates, so you can update the dots or add new dots in every frame without recalculating all the stuff, and that's fast, because then you need to pay most of this price only once, and not all the time and all the time and all the time. And also you can change this algorithm, but this is different from mine. But it's visible that you can change it so that it's stateful, but it's a tough job. Okay, I hope this was useful. I hope you find yourself thinking, okay, maybe this would have been useful in that and this situation, or I could use this as a building block, or just this makes me think what I could make my building blocks like, and so on and so on. That's the point of this presentation. So in the end, I just want to go and reach to this other topic, which is not performance related, but debugging is really useful with this tool. So, ObjConsolog, I call this geometry debugging on steroids. What's the goal? You want to debug geometrical algorithms like these, and you can say these are reasonably complex. You can make them bad, like it's easy to make mistakes and bugs if you are not paying attention, of course. Unit tests help, but of course you can see that there is a problem, but you need to analyze the problem. And you want to maybe visualize or better analyze the intermediate results. But you don't want to implement crazy debugging into your application. Like, of course, we can implement like a debugging mode in our application where if we know the good key combination, many older engines had this, if you know the key combination, you get a debug mode and you can move vertices one by one. It will write the coordinates, it will show the normal vectors or whatever, I don't know what is needed. But the problem is that it's hard to write that like that, and we only want points, lines, triangles, very simple stuff. And as you can see, this is not just an idea, this is in sdlib/src/utils/ObjConsolog. So this is not below the utils/performance, but just utils, because this is not really performance related. So there are alternatives. As I mentioned, you can develop your debug views, a lot of work. Who knows what is the programming or developer experience when using that. You can maybe use a GRTF for other scene exporter and export the whole scene. That kind of works, but you get a lot of trash, like there's data that you don't need. There is a lot of unnecessary data. There are transformations that maybe the exporter is doing so that you are not seeing the data that your algorithm is seeing, and you end up in this thinking that, oh my god, maybe the exporter merged these 2 points into one and I don't have it, I have it separate. And so that can confuse you a little bit. And of course you can always just use the debugger, that's the simplest, but then expect a lot of drawing on paper, fiddling, looking at coordinates and all kind of stuff. And if you have a lot of data and you just have your issue then, manifesting then, this can grow very hard. So what's the idea? From the name you can maybe guess. The OBJ file format is really simple. I already know it well. Actually, I wrote import s, export s for it in C++ many times, so I know it from inside out. But it's, even if you don't, just reading the Wikipedia page, you can, for this thing, you can learn it in like 15 minutes or less. And the idea, why we don't just log into the console, like literally an OBJ file, we should log into the console. Just the vertices, the triangles, the lines, and everything. That's very simple. It's easy to do. You can always log. And this is what I started to do, like not in this project, but like other projects as well, and other code bases. And I always did this, so I started to write a solution for this. So it's not manually console.write and everything, because of course for vertices it's very simple, but if you want something more like triangles, it's just handy to have a tool that automates this. And then I usually used Vim macros, not micros, sorry. You can imagine other scripts or something, but I use Vim macros that I took the whole log, I saved the log into a file and run the Vim macros on it. Then it would make the file literally an OBJ file because it threw out the trash that is not related to the OBJ logging, just other logs. And it also reformatted everything, so it took out the formatters and the logs, what is the file number and what is the line number and everything like that. So yeah, those macros, and then I just loaded it in Blender because there I have very clean UI, I know what it is, and it's literally the data that my algorithm works with. at the points where I am logging it. Okay, what features should this ObjConsolog have? 2D and 3D points. I separated the two, but it's unnecessary. Lines and paths, triangles, and also triangles with normal UV values, and nothing else. Oh, of course, something else more. Named objects. So you can say from this on, every call will be ending up in this named object. So you have separate objects in your Blender file after you open that. How to do it if you already use this ObjConsolog? You use the functions in the ObjConsolog. I will not explain all of them detailedly. You start your app. You have this setup. You start your app, do your thing. You save text from the console, or maybe you redirect it to a file or something, and you use this tool that is from the Magos IT GitHub, or you can use your own Vim tricks, but I wrote this tool in Python after a while, and then that's it. You can import the file in Blender. Very nice, very clean. And there's some finer words is that this is immensely useful for my case. You can see which vertex has which coordinates, how it looks, face orientation is normal, so read the coordinates of some buggy vertex or face that you know it's always buggy, but there is a bunch of data and you don't know which is which. So it's much easier this way, and hopefully this is as useful for you as it was for me, considering this and also all the others that has been presented in this presentation. And I just wanted to show some images. Geometry, I just loaded Blender. Look how the face orientation is, if it's like badly oriented. I can zoom in and see rounding errors. I can read the coordinates of face vertices where I know the face is buggy. You might know this image somewhere. And that's all. And this concludes my presentation, and I hope you enjoyed my presentation. And I also hope that this was not only informative, but also a little bit of training how to use building blocks in the case of optimization also. Generally too, like how to make a better architecture by using generalized codes and reuse codes, not just write them always in separate places. So maybe that's also fascinating in this sense. But most fascinating is maybe that you can also think in building blocks when thinking about optimization. And that concludes my talk. Thank you for listening. Bye bye.